Okay. Here. So we're going to continue with control theory today, and we're going to basically focus on. What is this here? Okay. So we're going to focus on the mathematical representation of a system using the impulse response and the transfer function, and then after that I'll go into two canonical systems. Canonical meaning that many systems can be represented in this form, what's called a first order system and a second order system, and we'll kind of understand how to model these systems based on the transfer function and what it looks like in the time domain. And there are of course higher order systems, but if you can somehow reduce even a complicated system into first order or second order, then you know a lot about it, because these are very well studied and they have some pretty intuitive explanations of what's happening, and I'll try and explain that as we go along. Wanted to add that for the multiple input multiple output system from last time I had I put some corrections or in Piazza, so please take a look at that. Okay, let me come back to the impulse response over here. So we consider an LTI system. So this is the LTI linear time invariant system, and we almost always assume it's causal, which means that there is nothing happening before time 0, and second, we assume that it's in equilibrium at time 0. So we define at time 0 to be, at that point everything is good, okay, and you can think of it as time 0 as being chosen at a point in time where something bad happens. Typically disturbance comes, some kind of bad thing happens, and then we want to make sure that the system responds nicely, okay, at that point. So it's okay to assume that when this thing happens, when this whatever happens, we're going to be at equilibrium at that point in time already. So that's the assumption we make. Of course you can relax it, but it makes things more complicated. The other thing I want to point out, that when we open up the system, we typically have the plant, and we have in the plant we have over here the disturbance W, and then we have the controller, and then before that we have the input U. And what I want to do is to essentially look at the modeling of two parts. One is this whole thing, which I'll call the entire system, versus modeling only this over here, okay. When we look at this whole thing, if you draw a box around here, actually the input to the system is not just U. Actually this is R over here, not U, this is U over here. The input to the system is not really U, it's basically over here. If you look at this input, this is U plus W, okay. It's the input control plus the disturbance together is what's going into the plant. So if you want to look at the modeling of the plant, what you really have to do is how the output Y depends on U plus W, okay. That's basically what I want to say. So the plant has some response to U, but we really want to know how it responds to the combination of U plus W, because that's really what's coming into it. And when we model the web server in just a moment, you'll see that this is what we have to do, okay. So having said this, let's look at what the impulse response is. So the impulse response is defined to be, it's the signal which is the output of the system when it's given a sharp delta input at time 0. So basically you take something and you kick it very hard at time 0, okay, with infinite power and unit energy, and when you do that, what's going to happen is it's going to respond with its natural response, okay, and that's the impulse response. So this is the signal which is the output when system is at rest. So you have to start with a rest, and input is delta, okay, which means it's at time 0, okay. So we know that if let's say the impulse response is given by g of t, okay, if that's the impulse response, then we know that for any input xt or any input ut, So if you do, no matter what, so if this is the impulse response, then for any input ut, yt is going to be ut convolved with g of t. Okay, so that's basically it, and we've actually used this fact several times in the chapter on transforms, where we said modeling a system, analyzing a system, where I would give you the impulse response or the Laplace transform or the Fourier transform of the impulse response and say, okay, now compute yt. Well, what you do is you just use this convolution step over here. Now, this requires convolution, which, as we know, is not very nice. So the impulse response is it is a good model for a system, for a linear time invariant system, but it's not a very useful one. Okay, it's accurate, but it's not very useful because it's hard to compute the convolution. So basically, we don't use it. Okay, it's just there, but we don't really use it. Instead, what we do is to go straight to the transfer function, which I can now actually finally define for you. And in our case, we'll define the transfer function to be basically the Laplace transform of the impulse response. Okay. So earlier I had used the term capital H to be sort of in quotes transfer function, where I said that the input is something, the output is something else, and we had sort of used this like, you know, yt is equal to h of xt, where h is this function that takes some input signal and converts it into some output signal. But now we can be more precise, because now that we know what a Laplace transform is, we can now say more precisely that the Laplace transform of gt is given by g of s using the standard notation. And so we can say that y of s, which is the Laplace transform of the left hand side over here, is just going to be u of s, g of s. So we just see that we've converted the convolution into a product. And so the output, the Laplace transform of the output, is just the Laplace of the input multiplied by the transfer function gs. Okay, and that's basically it. So we have taken the system analysis and made it really straightforward, because we can just take any input, find its Laplace transform, multiplied with the Laplace of the system gs, and we're done. So the transfer function that we talked about earlier here was really, you know, you can think of H as being some kind of, we're not really modeling the plant at all. Okay, we're just saying yt is H. So H includes inside it, I guess, all of the G and so on and so forth. So H in really is this part over here, right? If you take X, there is U actually. So this would be something like H of U of t. Okay, we are presenting the convolution using the operator H, but you know, that's not really a transfer function, because transfer function is always in the, we use it always in the Laplace domain. Yes?
Are we talking about LTI systems?
Yeah, we're always talking about LTI. So we're assuming for entire discussion it's LTI, it's causal, and it's equilibrium at time zero. So that's the first thing I said. Yeah.
So it means for an LTI system, transfer function and the impulse response are the same?
No, the impulse response is in time and transfer function is in frequency. So impulse response is is g of t, whereas the transfer function is g of s. So I should write that down. This is the transfer function. And that's why we distinguish between the two. The impulse response is a time domain function and its Laplace transform. So what I was commenting on was that earlier I had used the term H for the quote unquote transfer function, and it's not really the transfer function. Okay, this is what I called earlier, and I've always been careful to distinguish, and I always say, it's not really a transfer function. So because I want you to know that this is really what people call transfer function. That's just a convenient thing we use to understand the properties of an LTI system without having to know what a transform is. Okay, and it turns out to be, in the way you teach, it's easier to explain things that way than to go into transforms right away. Okay, are there any questions about this so far? Okay, so right, so what do I want to say over here? Right, so given this, I'm going to sort of again wave my hands a little bit about stability, because it's a very important concept and I want you to see it a few times. So here is where I'm going to talk a little bit more about stability. So we have this thing ys is equal to us gs, and quite often we can write down this one gs as being in the form ns by ds, where ns and ds are numerator and denominator, and they're polynomials, and n and d are polynomials in s. If they're polynomials in S, then what I can do is I can write this, and we can let's say the roots of ds are alpha 1, alpha 2, alpha 3, etc. Then we can usually write this down in the form I should say a over s minus alpha 1 plus b over s minus alpha 2 plus something like that, where a, b, and so on are basically complex coefficients. And then if you take the inverse transform, we get something like a e to the minus alpha 1t plus b e to the minus alpha 2t plus etc. Okay, and these are going to be all decaying down to 0 as long as these alphas are going to be in the are going to be positive, I guess, or it should be a to the, because I put s minus, it should be plus over here. So we need, if the alpha I are less than 0, then I should say real part of alpha I is less than 0, then decays. Okay. So just watch this step here. All I'm saying is I have a bunch of exponentials. Each one of them we want to go down to 0. For those to be true, the real part of alpha, okay, has to be less than 0. This is when we studied the complex exponential function. If you remember, it's basically this spiral, right? If it's a spiral in the real imaginary space, and we want the spiral to kind of go down to 0. Okay, certainly you want the projection of it to go down to 0 in the real axis, because that's what we see in the real function. We don't ever see the imaginary part, and so that happens when the real part is less than 0. Okay, so in just these few steps, you can see right away how we make sure the system is stable. What we have is some function gs, which is the transfer function, and if you put it in this form, the numerator denominator form, and we find the roots, then we have to make sure that the roots are going to be in the left half plane. The real parts of the roots are negative, or that the roots are in the negative half plane of the real imaginary plane. Okay, and that is the condition for stability. And if it's not in the left half plane, it's on the imaginary axis, we get oscillatory behavior. And if you have even one root on the right hand side, then you're going to get exponential behavior, okay, exponentially increasing behavior rather than exponentially decreasing behavior. So all this comes basically from the form of the transfer function. So what we want to do then is to choose the transfer function gs of a control system to be such that this happens, so that all the roots are placed in the right place. And that's what's called pole placement. We want to place these poles, because that's when the value of the Laplace transform goes to infinity, right? Each of these is if you remember, the value of the function, the value of s for which the value of the Laplace function is infinity is called a pole. So each of this is a pole, and the poles correspond to the roots of the denominator polynomial. And if you want to make sure that the poles are in the left half plane, then you'll get a stable system. So you want to choose. And when we do the system design, we'll choose it so that it's in the left half plane, and we'll study how to do that, basically in a couple of lectures from now. Okay, but that's sort of the big picture over here. So we've gone from the Laplace transform to the mathematical modeling. If we've gone from the mathematical modeling of the time output from impulse response using the Laplace transform into the transfer function, and the transfer function allows us to write the output in this form, which then allows us to intuitively see that the way we get a stable system, a good system from our perspective, is to choose the gs, is to play so that the poles are in the left half plane. Okay, that's sort of the summary. Now I haven't made this very precise, but I will when we talk about stability later on. Okay. So are there any questions about this over here? So one thing I have left out is how we get from this roots to this, and that's the partial fraction expansion, which I asked you to read. So that's in 812, and I'm not going to cover that because it's pretty straightforward. but I'm assuming that you will know how to do partial fraction expansion. But no matter what the denominator is, we can always find a partial fraction expansion because of the basically every polynomial can be factored, so you can always do this. Okay, that always is going to be true. Okay, are there any questions for this? Okay, right. So let's try and do a transfer function model for the web server, and so because that's the sort of the running example I've been using. And if you remember, we had this client, and we had a buffer, and then we have the web server. And we're assuming that the client is getting back some feedback of the state of the web server. The state is basically X, which is the buffer occupancy, and this buffer is B. And the client is sending input at the rate U, and we are saying that there's some kind of disturbance W, where this disturbance W is actually modeling the variation in the web server's service rate. So instead of saying the web server takes different amounts of time in order to process a request, it's equally valid to say that the web server processes jobs at a constant rate. However, there is this other load, W, which comes and goes, okay? And it takes away some of the cycles of the web server. And consequently, we're going to get a variability in the service rate of the web server, okay? So, I mean, it's a very useful transformation to use, and you can use this many other places as well, where the variability in a service can be transformed into a variability in the what's called the cross traffic. In networking, we'll call this cross traffic. And we'll make the server deterministic and the cross traffic stochastic, and that's the same as having a stochastic server. Okay, so to give you an example of this, I mean, it's like saying that, you know, the person at Tim Hortons who's serving you and giving you coffee, you could say the person always takes exactly 30 seconds to serve you, and it takes longer to serve you or to serve anybody else because there is this extra person, sort of a virtual person who's getting extra jobs, okay? And the extra jobs are going to be taking away time, so it takes you longer, okay? This is roughly what's going on over here. I chose to do this kind of modeling because it makes the form of the system particularly simple, because then we can say that x dot is basically going to be u minus w, okay? So to understand this, let's just say w0, basically then the web server is going to be not serving anything, because W is going to be sort of the variability in the service rate, right? So when the web server is not serving anything, then W is 0, right? Then the buffer is going to grow at the rate U. Well, obviously that's true because I'm pushing stuff into the buffer. Now, it's not exactly obviously true. You have to remember this is only true in the linear portion of the buffer, okay? If the buffer is already full, then x dot is 0. Even though I'm putting in data at the rate of U, x dot is 0 because it's full. It's just dropping everything, right? So this is a linear approximation. And as I said earlier, all systems are going to be nonlinear when you look at it. And the reason is because a linear system says that if the input is multiplied by a factor of 10, the output is going to be multiplied by a factor of 10 as well, right? But no matter what system you have, at some point it's going to saturate, right? You push hard enough, it's going to just break, okay? So you can't ever have a linear relationship between input and output. It's always going to be for a certain range of inputs, okay? So we're going to focus on that range of inputs where the system is actually linear, because otherwise we can't really use linear system modeling and then it gets complicated. So this is the linear approximation, and so we choose the operating point such that in the neighborhood of the operating point it's going to be linear, and then we can use a Taylor approximation if you want to approximate it. But in this case we don't need a Taylor approximation because the system is actually linear already. Could you shut the door, please? Or somebody, Raymond, thank you. So now what we do is that I want to make it even simpler because I want to essentially get rid of this u minus w. And if you recall, I said we want to somehow incorporate the disturbance into the input, and we can do that by having this virtual input v equals u minus w, and v can be thought of as the sort of the net input, and then we just say x dot equals v, okay, where v is going to be some variable function of time. And so to compute the transfer function, I want to compute the transfer function of the input that takes disturbance into account. We take the, so we have s of xs is going to be vs, and so we say that xs is equal to 1 over s vs. Now in our system, yt is equal to x. So the output, okay, the quote-unquote output of the web server that we care about is the same as the buffer occupancy level. So we get that ys equals 1 over s vs, and so this becomes the transfer function at 1 over s. Okay, because we're saying the output is 1 over s times the input, where the input is taking the disturbance into account. And so that's what we have over here, right? And so it's a very, very simple transfer function. It's just saying that, you know, ys is 1 over s vs. And as we'll see in later, it's going to be what we would call actually I should be more precise. The Laplace transform of x dot is actually s x s minus x x of 0, okay? But we know that at time 0 system is in equilibrium, and we'll define x of 0 to be 0, okay? Because we always start with x, so that's why that x of 0 term goes away, and that's why I can just directly write sx is equal to vs, because I've taken out the x of 0 term. Okay. And again, this is the assumption the system in time 0 has nothing in the buffer, which kind of makes sense. We started out the system, there's nothing in the buffer, we didn't do anything, it's causal, nothing happened before 0, so we're going to have x0 equals 0, and that gives us this particular form over here. Okay. So the Homburg question was this. We had a system where the velocity of the car is given by ax plus bx dot plus c x double dot, or dx squared by d squared x by dt squared. Thank you, Nabil. And so what is the transfer function? Well, to take the transfer function, we just take the Laplace transform of this. So we say v of s is going to be a x of s plus s x of s. And then x of 0 goes away because it's 0, right? Equilibrium system, plus c s square x of s. And this can be written as a plus s plus, bs plus c s square x of s. And so this is going to be the transfer function. Okay? And that's the answer. So a plus bs plus cs square. And you can see it's pretty straightforward. You have the Laplace table. It tells you what to do. Okay, so I hope everybody got that. Okay, any questions? Yeah? Wait a minute. So vs, no. We're saying that vs, see, output is going to be the transfer function times the input, right? So it's not 1 over. By definition, ys is going to be gs us. This is the transfer function, this is the input, and that's the output. And we just, substituted x for u and b for y.
So how's it different from the web server?
In the web server case, we had, how do we do that now? So in the web server case, we got ys equals vs by s, right? Because we had sys, we had x, the y was the buffer, right? Y is the buffer size. So we had basically y dot t equals, okay, v of t. And so we had on the left hand side sys equals v of s. And so ys was 1 over s vs. If you look at it over here, the velocity is, we're not taking v dot, right? We're just taking v. Okay, so that's why you're getting it in this form. It's not 1 over. Okay, so now we're going to kind of take a little bit of a detour and look at what I call first order and second order systems. And these are what we would call as simplified canonical systems. So we're going to just ignore, modeling a real system. You're just going to just forget all of that for a moment and just say, okay, here's two systems, and a first order system and a second order system which have a particular form of the transfer function, and we'll study what the behavior of the system is because of the transfer function. And then later on, what we'll do is when we model a real system, we'll try to make it look like a first order system or a second order system, because if you do that, as I said, you can get a lot of insight into it. So without further ado, let me just talk about a first order system. And the first order system is defined, so these systems are all defined by their transfer function. Okay, and we don't, at this point, we're not going to ask where the transfer function came from, but I'll give you a hint in just a moment. Here, the transfer function g of s is given by k over 1 plus tau s. Okay, that's the definition of a first order system. And if you remember, we had this 1 over s, so that's sort of in this form, k over 1 plus tau s. It's not actually exactly in that form because of the 1 plus term. But anyway, so you look at it and say, great, what does it mean? Okay. And what it means is that we can actually, the way we study these systems is to look at essentially a step input. There's really a couple of things we do. We look at the step input response. And the second thing we like to do is to compute the final value. Okay, to the step input response. So we want to say, okay, I have a system and I'm going to give it a step input. Rather than, so giving a delta input, I'm going to give a step input and I'm going to keep it going at that point in time. So I'm going to push it with a unit value and then keep pushing at the value forever. What does the system do? Okay, and we do that instead of a delta because you can't do a delta in real life. Okay, and whereas the step is easy to do, right? And we can also measure the output easily, and in the transform domain, delta and step are very closely related. The step response, the Laplace transform of the unit step is 1 over s. Laplace transform of delta is 1, and so we can easily deal with either 1 or 1 over s without too much trouble. Okay. Now we have particular terms, so we call k as the gain parameter. And we call this tau to be the time constant. And we'll see in a minute why that's true. Okay, so the notion of a time constant is extremely important, and we can view the time constant as being essentially an inherent quality of the system, of any control system. It's the sort of the time in which it sort of behaves, okay? And intuitively understanding the time constant of any system is very important. To give you a specific example, to make it illustrate very clearly, imagine you have a big battleship, it's going on the ocean, it's going along very fast, okay? It's got enormous mass going like this, and if you say, okay, turn right, okay, it takes a while, it's going to slowly turn, okay? And so if you say turn right, it can turn right, but it's going to maybe take 5-10 minutes for it to kind of slowly turn right. Imagine that a mosquito that's buzzing along in the on the deck of that aircraft carrier battleship. You say turn right, it goes right. It's instantaneous practically, right? Within a few milliseconds, it's turned right. Why? Okay, why is it that one can turn right away and the other turn takes a long time to make the turn? It's because they have different inherent time constants. Okay, from the perspective of the system, they have different inherent time constants. It has to do with the mass. It has to do with the inertia. And so if you have less inertia, it's very zippy. It turns right away. It's same thing. If you have if you're driving a truck versus if you're driving a bicycle or a sports car. In a sports car, you turn the wheel and whoop, it just turns right away, right? Whereas if you do that in a truck, nothing will actually happen. It will take a long time for it to turn. And so in many cases in computer systems, we have to appreciate the time constant. In computer networks, the fundamental origin of the time constant is the round-trip time delay. Okay, why? Because whenever we do something in the network, we actually don't know it happened or not, right? You do something, and you'd better get a response back saying it happened, right? So we do something, get a response back. We do something else, get a response back. So that takes time. How much time does it take? It depends on the speed of light propagation delay. Okay, the speed of light is not fast enough. Okay, it's just too darn slow for us, okay? Because we can do operations. I mean, why do I say that, okay? I mean, just think about it. How many operations can you do? If you have a 2 gigahertz processor, how many operations can you do in 1 nanosecond? Right? You can do 2, right? So clock cycle is 1 nanosecond, so 2 gigahertz, 1 nanosecond, you can do. How much distance does light travel in 1 nanosecond? 30 centimeters. It goes about this much. Okay, it's about this much in 1 nanosecond. So the light, the photons are going like this, and already you computed 2 operations. Okay, that's not bad. So if it's going from here all the way to DC and back, okay, you can do about 200 operations. And if it's going from here to China and back, you've done lots of operations. Okay, that round trip, speed of light propagation delay is about 140 milliseconds. Milliseconds. In 140 milliseconds, you can do 140,000 operations. Okay, you can do a fast Fourier transform by the time you get a message to China and back. Okay, I mean, that's a lot of computation. So for us, if that operation means send a bit or send a byte onto your output queue, which you can, then by the time the first bit gets to China, you've got 140,000 bits already on its way, and the web server in China says, hey, it's too much. By the time it says it's too much, it's got 280,000 bits piled up on its head. Okay, not good, not good. So what do? You send a bit, you say, are you okay? Comes back, says, okay, here's a little bit more, and what do you get? You get the sawtooth going up. Okay, fine, oops, too much, and you go back down again. That's what you get TCP. That's what TCP is doing. What's the fundamental time constant? It's the round trip time. It's the propagation delay to go from one end, and for, yeah, okay, fine, go ahead, give me some more, come back. And so this is the fundamental time constant in the computer network. And you can't get around it. It's going to be there no matter what. So if we are trying to do any kind of operation that could be far away, the round trip time constant to go to Mars is about 8 minutes. Okay, if it's very close to you, and if it's on the other side of the sun from you, it's up to 80 minutes. Okay, so you send a command to the Mars observer, 80 minutes later say, yeah, I got it. Okay, you can go have a cup of coffee, come back, and then it says, I got it, right? So you've got to be extremely careful what you do in these kinds of systems. Hopefully, this gives you some idea what time constant means. It means there's something intrinsic to the system that you can't change, and it shows up right away, both in the first order system and in the second order system, in the transfer function right there, tau s. Okay, that's really the intrinsic time constant. I'll explain what that is mathematically in just a second. To understand this, we're going to take a step input. So let's say that u of s is going to be 1 over s, because u of t is equal to basically the step input. So this is going to be you're at 1, okay, and this is time, and the signal value is 1 at this point. So we know that u of s, the Laplace transform is 1 over s. Then we can say that y of s, the output, is going to be nothing more than 1 over s times k over 1 plus tau s, because ys is input multiplied by the transfer function. And we can rewrite this using the partial fractions as k times 1 over s minus tau over 1 plus tau s. Okay, and that step I'll leave for you to figure it out. And this you can write as basically k over s plus k tau 1 plus tau s. And this turns out to be yt, if you take the inverse transform, equals k times 1 minus e to the e to the t by tau. There's no minus, the e to the t by tau. Sorry. Is there a no minus? I have to remember this. Let me see. So 1 plus, there should be a minus here, right? Minus 1 minus e to the t by tau. Yeah, it's going to be minus, otherwise the graph won't work. So I have yet another mistake. Beg your pardon?
I posted this on Piazza.
You put it on Piazza. Oh, thank you. Yeah, it is a minus over there. Okay, when you're writing thousands of equations, some things creep in. Okay, so First of all, let me just walk through this before I draw the graph. So this is the step input, right? So that's by definition. This is the Laplace transform, the step input. That's from the Laplace table. If you're an engineer or if you're a mathematician, you do this in your head to compute, the integral. This is by definition the transfer function, and this is from partial fractions. So to understand these 4 steps, you need to know definition of step input, Laplace transform, transfer function, and partial fractions, which by now hopefully all of you understand.